Hello student. Now I'm going to start lecture 3 on fluid statics, right? So students, what's the lecture name? Lectures 3. Students, lecture 1 and 2 already I uploaded, right? So this is lectures 3 students, it's not 2, it's lectures 3, right? In this lecture, what I'll discuss, I can see before going to start lectures 3, just I wanted to recall what we did in lectures 2. Students, in lectures 2, I taught you what is the effect of, you can say, temperature on density, and second concept is their effect of pressure on density, right? So now students, I'm going to teach you, it's literally highly important students. So what is the concept, students? This is which I'm going to start now, student. This is the student, the concept of pressure, the concept of pressure, right? Okay, students, here I can say what is the things which you can keep in your mind. Students, a fluid or gas placed in a closed volume can be subjected to an external force. What is, students? I'm writing one time for your sake of convenience. What, my dear? A fluid or gas placed in a closed volume can be, students, can be subjected to an external force, you can say, sir, this point is not much clear. Wait, student, I'll elaborate in detail. So here, students, for understanding which I said, as I'm going to explaining you behalf of diagram, right, my dear? Okay, so to understand these things, students, for example, I'm considering the situation, right? So we can say this is the container, student. This is the container, right? In this container, students, this is filled with water. If I'm not telling any name of the liquid, so you can take, this is what, my dear? Only water, right? Okay, a fluid is filled in a container and its top is, a fluid is filled in a container and its top is closed by a smooth light piston. What is, student? A fluid is filled in a container and its top is closed by what, my dear? You can see this is smooth light piston, smooth light piston, students, smooth light piston. Okay, fine. Now, students, which I have taken consideration, right? Students, here I'm going to apply a constant force on piston. What is, student? Here I'm applying constant force which is equals to F. This force is constant in magnitude, right? So students, a constant force F is applied to the piston, after that, as piston and fluid are in equilibrium. Students, if once you apply force on a piston, then what you can say, initially not, after some time, what you can say, students, this piston is in equilibrium. What is the meaning of equilibrium? Means, students, you can say, we can say that fluid also exert the same force in upper direction on piston. Students, if we will make FVG of piston, students, if you wanted more clarification, then what you can say, this is students piston, so I can say, student, this is FVD of piston. So this is external force. This is what, my dear? External force applied on the piston, right? So if you can say entire system is in equilibrium, and students, you can say at equilibrium, what is, students? At equilibrium, we can say fluid also, students, you can say here, fluid also exert the same force in what? Upper direction. Due to this, what you can say, piston is in equilibrium. Piston is in equilibrium. So at equilibrium, we can write applied force in downward directions, and this is what? Force on piston. Due to what, my dear? Due to fluid. Due to fluid. Okay, students, for more clarification, right, I'm going to take another example. Let us suppose this is same container, students. I'm here again considering same container, right? So this is container filled with liquid, and top of the container there is a piston, and same thing which I applied, same force. I'm drawing more diagram for better clarification. I'll take here another things, students. Here entire, you can say, student, here entire container filled with water only. Here, students, I'm considering students, here I'm considering, this is what you can say, imaginary spherical water droplet, right? Inside droplet, students, I'm considering a cubical volume of fluid. Students, I'm considering here a cubical volume of fluid within its volume, right? So now, students, I'll take this imaginary sphere outside, and I can explain you more about what is the things which you can analyze, right? So now, students, this is imaginary sphere. Inside this, what? A small cubical volume of a fluid. Small cubical volume of a fluid, right? As students, what you can say, this is also in equilibrium. Why students? Because this is small cubical surfaces contact with the liquid. This is the small cubical surfaces what contact with the liquid. So what you can say, due to this small cubical volume also in equilibrium. So due to this, students, you can write forces, neighboring forces which is acting on, you can say, my dear, this is small block. This is what remains, what you can say, must be net force on it must be 0. Due to this, what you can say, this small cubical volume surfaces within its I can say imaginary spherical volume must should be in equilibrium, because net force on it must should be 0. There must be some internal forces, right student? What you can say, because this is the things which I kept it out from here, so what you can see student, there must be some internal forces present on its volume. Student, there is some internal forces present on its volume. As we know, when some internal forces, what is students, as we know, when some internal forces are developed within the body, if there is some forces developed students within the body, then student, what you can say, in solid, we account of these forces in the form of stress. Students, if you remember, recently I taught stress and strain, right? So in solids, because there is a forces, that force is what students you can say in the form of stress in the solid body, and the tangential component of these forces are account in the shear stress, which produces what, shear strain. Okay, now students, there is one point which you can keep in mind. What I said, I'll repeat again, just keep in mind student, what I said to you student. I said in solids we account for these forces in the form of stress in solid, right? And tangential component of these forces, what you can say, account to be shear stress, which will what, develop and generate shear strain. That is not a part of what you can say fluid students. So here you can write one note. What, my dear, in fluids there is no tangential, there is what, my dear, no tangential component. There is what, student, no tangential component, right? So again you can say, sir, what is this? Students, for explaining these all points, again I'll take another example, right? In static fluid, internal forces are normal to the what, bounding surfaces. Then students, you can say what I see the students, internal forces in static fluid normal to the bounding surfaces, right? We can see that the force external by the surrounding fluid on a small cubical volume are balanced and normal to its what, surfaces. Student, what I have taken, this is the what you can say hypothetical situation. This is hypothetical, right? This for understanding if something inside the water, how this particle is in equilibrium. That's all. There is no any such big deal how it came. Now students, actually what is I said, in fluid there is no tangential component. For explaining this thing, again I am going to draw another example. So take a snapshot. I hope everything is visible for you. Okay, take a snapshot students. Okay, I hope you already taken. Now students, I want you to turn the page to start the next topic. So students, here on the basis of similar concept, we can explain the equilibrium. Let us suppose students, again I'm considering another situation, right? Students, here again you can say this is container, this is what, my dear, container, right? So students, here students, I'm considering a situation of floating body. So you can say this is the floating body, right? And entire container, students, you can consider filled with water. Filled with water, right? Okay, on the basis of above, that means this one which I explained previously, on the basis of above result, we can explain the equilibrium of this floating body, right? So students, here we can see, that on the surface of submerged, what is student? Here we can see that on the surface of, what, my dear? Submerged part. Submerged part of the body which is in contact, with the liquid molecules. Now students, here you can write what I said, because here you can see, students, submerged part of the body which is in contact with the liquid molecules, and the liquid molecules exert normal force at every local point. What, students, you can say, everywhere. You remember basic concept of kinematics, student, right? Or I can say NLM, normal force always acting, what, my dear? This is perpendicular to contact surface. So you can see this floating body in the contact of what, student? This floating body in contact of water molecules or liquid molecules. So what you can say, these are the normal forces. What, students? These are the normal forces acting on this, what you can say, floating body. Now students, why? Because this is an equilibrium. This floating body is what? Equilibrium. So weight of body is balanced by what? Vertical upward components of all normal forces. Okay, how, students? Just have a look. Students, I'm going to make a video of this floating body, right? Students, I'm going to make, this is FVD of what, my dear? Floating body. Okay, fine. Students, here, let us suppose you can make, this is the surface is the floating body, right? Students, every normal force acting like this, students, you can see this is surfaces. So everywhere, this is what you can see, direction of what, my dear? This is, you can see, direction of normal forces, like that. Okay, student, if there is directions of normal forces, so students, here I'm considering one normal forces. Let us suppose this is what normal forces which is acting on the body. What, my dear? Which is acting on the body. Okay, so this is, students, I'm calling, this is the normal force, because normal force on the surface of floating body due to water molecule. So normal force, students, or I'm calling this is F, right? For better clarification, let us suppose there is force which is acting on the layer of floating body in this direction, and this force making angle theta from vertical. So students, here I'll take a component, because force belongs to quantity vector, so you must take what? Components. Students, you can say, what is this component, my dear? This is F cos theta, and this is what, my dear? This is what you can say, this component. This is what, my dear? You can say F sin theta. Students, F cos theta is what? Acting perpendicular to surface. So you can write, this is what? Fn is, it's a normal force. F sin theta, student, F sin theta, no, it's acting tangential in the surface. So you can see this is what? Ft. Students, let us suppose I considered force in these directions with respect to what? Vertical. So what you can say? F cos theta. This is what? F sin theta. Let us suppose you can take another example. You are applying force like this, right? Students, if you are applying force like this, students, again, this is theta. Extremely sorry, student. Now you can take component of this. What you can say? F cos theta and F sin theta. Students, we can say F cos is what? Adding with this component, and F sin in this direction. Due to this, students, as I said, in fluid there is no tangential component. I hope you got solution of this statement. In fluid there is no tangential component. Why? Because you can see, my dear, tangential component what? Tangential component cancelling each other. That's why I said weight of the body, what are students? Weight of the body balanced by what? Vertical upward component of all normal contact forces. Right, students? So here, due to this, just we have to avoid this ft forces on what? Liquid surfaces. There is no any contribution of this tangential forces on liquid surfaces. So always forever, what we have to consider for a liquid force is an perpendicular to contact surface. Now students, tangential component of these forces are what? Account to shear stress which produces shear strain. As I said, in fluid there is no tangential component. I hope you got my concern. Now students, in static fluid, internal forces are normal to the bonding surface. Students, I'll repeat again. In fact, I'm writing as a note, so you can keep in your mind. Students, in static fluid, in static fluid, internal forces are normal to the bonding surfaces. What is the normal to the bonding surfaces? Okay, fine. Now students, fluid layers, I can see this is node, this is 1, this is what, my dear? This is node number 2. Students, these are the theory points. The student, they can ask as a theory. That's how I'm covering all the points. Fluid layers, students, you can say fluid layers will apply force on each other only students, tell only along common normal, my dear. Only along common normal, right? Okay, so just keep in mind these are formulas. These are the theory points. Now students, I'm going to explaining, or I can say these are the mathematical discussion of pressure, right, my dear? So here I wanted to write final, what is the formula of pressure? So pressure formula I can write, a student, this is what? Fn upon what, my dear? It's a area. And what's the Fn, student? You can say this is F cos theta upon area. So now onwards, keep in your mind what is the formula of pressure. This is what, my dear? F cos theta upon area, or you can keep in your mind also like that. This is F normal upon area. Okay, now friends, these are the, I can say, definition. Now I can say I've finished just definition. Just imagine last 24 minutes I was explaining only how pressures can be filled in the mathematics, or I can say in physics. Okay, now students, this you can take snapshot. You can take snapshot. Okay, I'm giving you 20 seconds. Okay, now students, I want to turn the page because there are few basic points about pressure. So students, first I wanted to write it is a scalar quantity. That is students, this is a point about pressure, my dear. So you can say it is a scalar quantity. First point. Now students, pressure students, I wanted to talk on behalf of, I can say that is what, my dear, unit. So pressure student, yes, I unit I wanted to discuss, as well as CGS unit. So what is the definition of pressure? That is what you can say as SI unit, force per unit area. So this is what, my dear, first unit of SI unit of pressure, Newton per meter square. Second bit is what you can see, just multiply divided by Newton meter in numerator also, and meter in denominator also. So you can write also, it's not necessary, just keep in your mind, joule upon watt, my dear, meter cube. Point number third, student, what you can also say, these are the Pascal. So students, you can write in a one line. You can write, students, Newton per meter square is equals to joule upon meter cube is equals to what, students? Pascal, right? Students, for numerical, you can keep in your mind, for numerical students, we are always under this pressure. So this is 1 atm. What is 1 atm? Atmospheric pressure. Usually students, I wanted to connect one point at atmospheric pressure, student. It's what representation usually you can take, that is what you can say, P naught, right? Okay, now beta 1 atm, what you can write, this is beta 1 atm, you can write 1.01 10 to the power 5 Newton per meter square, right, my dear? Okay, students, again you can write 1 atm 76 centimeter of Hg. Students, also you can write 1 atm is equal to 76 mm of Hg. Last, students, you can also write 1 atm is equals to 76 torr, TORR. Here, students, keep in mind, 1 torr is equals to what, students? This is what, multiply by 10. 1 torr beta g, what you can write, 10 mm of Hg. So this is which I discussed, student. These are the points related to SI units only, right? Remaining what we have, this, students, I can say we have CGS unit. So what is the CGS unit, students? CGS is what you can say, Dian per centimeter square. Students, this is also true. Somewhere, students, rarely, majorly we are using this one only. Somewhere, beta, you can say this is also known as what? Vary. BAR. This is by A. So it's nothing but, beta, I can say again alternative name of what? Celsius unit of pressure. Right. Okay. And it's nothing, students. You can say vary is nothing but it's students equal to what? Dyne per centimeter square. So these are students again, these are the property, I can say pressure units. So take again snapshot. I wanted to turn the page. Okay, I hope you already taken. Fine students. So now I'm going to turn the page. There is a few basics points students which I want to discuss about pressure. That is, I can say last point for pressure. What is student? That is last point for pressure. So this is students concept on what, my dear? Concept on absolute gauge pressure. Concept on what? Absolute and gauge pressure. Okay, students, what is things? The excess pressure above atmospheric. What is student? The excess pressure above atmospheric pressure is usually called gauge pressure. Student, again I'm repeating, the excess pressure above atmospheric pressure is called gauge pressure, and total pressure is called absolute pressure. So students, I want to write formula of absolute pressure. So what is absolute pressure? It is a summation of what? Gauge pressure. Gauge plus what, student? Gauge pressure plus this is what, my dear? Absolute pressure. Okay, fine. Now students, note there is a points, here you can write mathematical formula. Gauge pressure what, my dear? This is gauge pressure. What you can write? Absolute pressure minus, I wrote wrongly beta, this is atmospheric pressure. This is atmospheric pressure. So gauge pressure is what, student? This is absolute pressure minus atmospheric pressure. Okay, fine. Students, absolute pressure, in note I can write for your clarification. Students, absolute pressure is absolute pressure is 0 in perfect vacuum. What is, student? Perfect vacuum. There is, students, one question here which I wanted to do here. Students, it's a theory question, it's not a tough, just logical. Students, gauge pressure what's option number first? Maybe positive, maybe negative. be 0 and last student all of this. Okay, so now students, I'm going to solve these questions. Okay, so what says first? Maybe positive. Yes, student, it's possible. Have a look. What's Gauge pressure? Gauge pressure is what? Absolute pressure minus atmospheric pressure. Students, if absolute pressure greater than what? You can say atmospheric pressure. So definitely students, what you can say, gauge pressure will be positive only. So you can see option first is correct. Now students, maybe negative. Yes, students, you can say if absolute value less than what? Atmospheric pressure, then you can say gauge pressure is negative. Correct, students. Now maybe 0. Yes, again possible. If absolute pressure is equals to atmospheric pressure, student, for that case you can say 0 also. So what is the answer? All of this. Students, so today class dedicated only definition of pressure, which I have said. If there is any error, not any point clear, then you can write your concern in comment box. I'll back to you. You can take snapshot. This is all about today class. I can say this is lecture number 3.